In this video, I'll be discussing Gibbs free energy and the various different ways to calculate it. So Gibbs free energy is symbolized by the letter G, and it's the last state function that you'll learn in thermodynamics. And it represents the external energy of a chemical system that is available to do work. So earlier you learned about enthalpy, delta H, which is the internal energy of a chemical system, and you learned about entropy, delta S, which is the disorder of a chemical system. Well, now we have Gibbs free energy. And Gibbs free energy is very important to chemists because it tells us when a reaction is spontaneous. So the value of Gibbs free energy for a reaction will tell you whether it's spontaneous or not. If your Gibbs free energy is negative, if it's less than 0, your reaction is always spontaneous. When your Gibbs free energy is equal to 0, your reaction is at equilibrium. And when Gibbs free energy is positive, when it's greater than 0, your reaction is always non-spontaneous. So Gibbs free energy has the final say on when a reaction is spontaneous and when it isn't. And there's a variety of equations that you can use to solve for Gibbs free energy. This equation here is a very common one, and it relates enthalpy and entropy with Gibbs free energy. Now, Gibbs free energy is somewhat different to enthalpy and entropy in that it's temperature dependent. So the temperature that your reaction takes place at affects the Gibbs free energy of the reaction. And so you'll take the enthalpy of your reaction minus the temperature multiplied by the entropy of your reaction to get the Gibbs free energy. And just as a note, these little degree symbols mean that this is happening under standard conditions. Now you can also apply Hess's law to Gibbs free energy, which means you can look up these Gibbs free energy values in tables for different compounds, and you can take the sum of your products minus the sum of your reactants, and that will also give you the Gibbs free energy for your reaction. Now Gibbs free energy can be applied to equilibrium problems. So for reactions that take place at equilibrium, we have these two equations down here, and they're used for different scenarios. So this first reaction would be used for when your reaction isn't at equilibrium, and its delta G is equal to delta G prime plus RT ln Q. R is the gas constant 8.314, and Q is your reaction quotient, which takes into account the concentrations of your compounds. And when you're at chemical equilibrium, you would use this equation here, where delta G prime is equal to negative RT ln of K, where K is the equilibrium constant. So you would use this equation when you're at equilibrium, and you would use this equation when you're not at equilibrium. Let's go ahead and look at some examples with Gibbs free energy. So we've got this question here, where we've got this reaction, where we have chlorine gas plus water, creating hydrochloric acid plus oxygen. And it asks us to calculate the delta G for this reaction using standard enthalpy and entropy values and using standard values for delta G at 298 degrees Kelvin. So first we'll go ahead and calculate it using this equation where we have the enthalpy and entropy values with our temperature. So first we need to calculate delta H and delta S so we can plug it into this reaction with the temperature in Kelvin. And I must stress, your temperature always needs to be in Kelvin for this to work. You cannot plug Celsius temperatures into this reaction. They have to be in Kelvin. But let's go ahead and calculate delta H and delta S using the values in this table here for our different compounds. So you should get negative 97.2 kilojoules per mole for your enthalpy value for the reaction. And you should get negative 168.64 joules per mole Kelvin for your entropy value. Now one thing you definitely need to keep in mind is your units, because to plug these values into this equation for delta G, your units need to match. They need to be consistent. As you can see, for enthalpy, our units are kilojoules per mole, and for entropy, our units are joules per mole Kelvin. So I usually find it easier to convert the entropy value to kilojoules per mole. And to do that, you'll divide this number by 1,000 to get it into kilojoules per mole. So let's go ahead and convert that now. So now that we have that converted, we can go ahead and plug it into our equation, plug in 298 for T, and that will allow us to solve for the Gibbs free energy. And once you plug everything in, you should get negative 46.9 kilojoules per mole as your delta G value. So now that we've calculated it this way, let's go ahead and calculate it using the standard values for delta G that are also in the table up here. So doing it with that method, you should get negative 50.3 kilojoules per mole. So this is the value we got using the equation up here with enthalpy and entropy. And this is what you get when you just use Hess's law and take the sum of the products minus the sum of the reactants for these standard values. And like I said, they are different values, but they're very close. They're very similar, which is good, which is what you want. Now we have to evaluate this. So remember what we said earlier about spontaneity when it comes to the value of delta G. So now that you have values for delta G, is this reaction spontaneous or non-spontaneous? Well, our value for delta G is negative, so we would say that yes, this reaction is spontaneous at 298 Kelvin. So now let's go ahead and look at some examples of Gibbs free energy being applied to equilibrium. So we've got this question here. So we've got this equilibrium reaction where hydrogen gas and iodine gas are at equilibrium with hydrogen iodide gas. And we've been asked to calculate the equilibrium constant K for this reaction. So we've been told that the reaction is at equilibrium because we're being asked to solve for K. And when you've been asked to solve for K, you're going to use the equation that we talked about when the reaction is at equilibrium. And that was this equation here, where the delta G prime of your reaction is equal to negative RT ln of K. And our goal in this question is to solve for K. So the first thing I would probably do is go ahead and calculate the delta G for your reaction, and we're going to use the table to do that. So just take the values from your table and use that to calculate delta G. And so calculating this using the table, we get our Gibbs free energy as negative 15.93 kilojoules per mole. However, we have to keep units in mind here because our equation involves the gas constant R, which has joules in its units. So we've got to convert these kilojoules into joules so that when we plug it into our equation, the units match. So multiply it by 1,000, and that will give you the joules per mole that we can plug into the equation, and the units will match with the gas constant R. And I didn't specify the temperature, but the temperature for this is going to be 300 degrees Celsius. So we also need to convert this temperature, 300 degrees Celsius, into Kelvin. So remember that Kelvin is equal to your temperature in Celsius plus 273. So if we add 273 to 300, we'll get 573 Kelvin as our temperature. And that's what we'll plug in for T. So now the first thing you want to do is, since our goal is to solve for K, we need to isolate K. So I would go ahead and divide this term to the other side, this 8.314 times 573. Divide that over here, and that'll get us one step closer to getting towards K. So once you divide it over, you'll end up with this term, where you have this fraction is equal to the natural log of K. Well, the only thing now stopping us from getting to K is this natural log. And the opposite of natural log is E, Euler's number. So to get rid of this natural log, what we need to do is raise both of the sides of this equation as a power of E, and that will cancel out the natural log. Let me show you what I mean by that. Now it's kind of hard to see here because of the font, but what we've done is taken E and raised it to the power of that fraction. So this is E raised to this as a power. And ideally you would simplify this fraction down and then raise E to whatever this comes down to as a decimal. And then you punch E into your calculator, raise it to the power of this fraction, and that will give you your value for K. So in this case you should get 28.3 as your K value after you solve this here. And remember, equilibrium constant has no units. The biggest thing I would say for these equilibrium problems is definitely keeping track of your units, making sure your units match, and also keep track of your signs. Because we have a negative in the numerator and a negative in the denominator, those two negatives are going to cancel each other out. So always make sure you're keeping track of your units and keeping track of your signs. So to deal with the other equation, this equation here with Q in it, this RT ln of Q, you would approach it in a very similar way, where you solve for delta G using your chart or using another method, and once you get delta G, then you plug it in, and ultimately you would have to calculate Q. So let's go ahead and look at this a little differently if we had to solve for, let's say, the delta G of the reaction, take into account the reaction quotient. So now our question reads, calculate delta G for this reaction, and this is regular delta G, not delta G prime, at 300 degrees Celsius if the concentrations of hydrogen iodine and hydrogen iodide are 0.4, 0.345, and 0.220 molar, respectively. So here we're saying that the concentration of H2 is this, the concentration of I2 is this, and the concentration of HI is this. And this is where we bring in the Q. So if your question specifically gives you concentrations, that's when you want to start thinking in terms of using this equation with Q in it, because we need to use these concentrations to calculate Q. So we're going to calculate delta G prime in the exact same way we did before with the table values, and we're going to convert it just like we did into joules per mole, but we also need to calculate Q so we can start plugging things in and make things a little more straightforward. So remember, you calculate Q the exact same way you would calculate equilibrium constant, where you take the products over the reactants. And in this case, you square HI concentration because there's a 2 in front of the HI. So remember, you always raise that to the power of its coefficient. And you should get 0.351 for your value of Q. So now that we've solved for delta G prime and we solved for Q, we know what R is, and T is given in the question, although we need to convert it into Kelvin again. Once we do all that, just plug in your numbers and solve for delta G. And so once you plug all your values in, you should get negative 20.92 kilojoules per mole. And kilojoules per mole is typically the units you want to show your delta G values in. And that would mean that our reaction is still spontaneous given these conditions for Q. So now let's go ahead and look at one last thing you can do with Gibbs free energy, which is estimating the phase change temperature for a reaction. So that means estimating boiling point, estimating melting point, estimating freezing point. You can use delta G to estimate the temperature at which a phase change occurs for a particular element or compound. So in order to do this question, for example, where you estimate the boiling point in degrees Celsius for benzene, so we've got liquid benzene going to gaseous benzene, and so we can modify the equation for Gibbs free energy in order to solve for temperature, and that's the temperature of the phase change. And the phase change is going to occur when the Gibbs free energy is equal to 0 for the reaction. So you set delta G prime equal to 0, and you rearrange the equation to solve for T. And that's what that would look like. Temperature of the phase change is equal to the enthalpy of the reaction divided by the entropy of the reaction. And that's how you rearrange it after you set delta G prime equal to 0. So basically you're going to take the enthalpy of this reaction using table values divided by the entropy that you take from table values, and you solve for T in Kelvin. So I'm going to go ahead and give you the values here because I don't want to copy and paste the table again, so you can see what they are. So I went ahead and did the math for you here, but you would look these values up in the table, and you would calculate the enthalpy of reaction and the entropy of reaction. And I would go ahead and divide the entropy by 1,000 in order to make the units match, make it a little easier. And you end up solving for T in Kelvin, and our temperature in Kelvin here is 353.03. However, the question asks us for the temperature in degrees Celsius, so that's definitely letting you know, always make sure you understand what units the question wants your answer in. Because while this is technically correct, we want it to be in degrees Celsius. So remember, if you want to go from Kelvin to Celsius, you subtract 273 from your number. And when you do that, you should get 80.03 degrees Celsius, which is the estimated boiling point for benzene, which is extremely close to the actual boiling point for benzene. So that's just another thing you can do with Gibbs free energy. And with that, that's about it for Gibbs free energy and for the semester.